Hello everyone, I'm Mark Tewksbury, your host for this program. Our goal is to reveal the methods and materials that turn out the products you see around you every day. If you think you know something about these items, you might be surprised. There's a whole new world of things waiting to be discovered here on How It's Made. Caffeine is not for nervous types, let me tell you. To get rid of it, green coffee beans are blown through water steam. The swollen beans are then washed in water to release solvents or active carbons. Finally, they're roasted. A decaffeinated cup of coffee contains 25 times less caffeine than a regular one. On today's show, holograms, package printing, skin culture, and canned corn. Printing variations of an image in layers, then having light reflected from those surfaces at different angles is basically how you produce a hologram. Sound mysterious? Not for much longer. A hologram is a three-dimensional photograph produced by the interference of two laser beams. A laser emits light, this light ray. The color of the light varies according to the wavelength. A shutter, when activated, either blocks the light ray or lets it pass through. Here the beam is split in two at a 90-degree angle. The interference of the two beams is clearly visible on this screen. It has very defined fringes. The beams need great stability because the pattern of interference projected on the screen is extremely sensitive to minute vibrations. A light tap on the table can easily spoil it completely. The team will create a hologram from this sculpture made of modeling clay. The sculpture is positioned on a support with a magnetic base which adheres to the metallic table. Then they place a glass in front of the object. Here's the exact point where the light beam passes. The table has to be perfectly stable, so it's made of a 2.2-ton block of steel, which rests on 18 air tubes. The table and laser are thus well insulated from all vibrations. The beam splitter separates the beam in two, directing one behind the object and the other in front of it. One part of the beam heads toward the front of the sculpture. The beam first passes through an objective lens, which diffuses the light. Then it's reflected by a parabolic mirror, which prevents it from losing too much of its intensity. As in photography, film is required. This holographic film is attached to a glass plate with adhesive tape. Then another glass plate is added so that the film will not move. A vibration of 1/10 of the laser's wavelength is tolerable. Now the laser is turned on. The intensity of its light ray reaches about 250 milliwatts. The normal exposure time of the model to the beam is about 1 second. But some holograms, made with a pulsed laser, are exposed to the light for 12 nanoseconds, an infinitely short period of time. Here we see the reference beam coming from the parabolic mirror. And here we see it from another angle. As in photography, the film has to be developed. These trays contain different chemical solutions and the developer. First, the film is soaked in the developer for 2 minutes. This solution blackens the silver salts, which have reacted to the light. Then the film is soaked in a solution called bleach to completely eliminate the silver salts, which blackened it. Now the film is rinsed. This step is used to eliminate the acids in the emulsion and to not contaminate the next solution. the film gently becomes transparent. It's then rinsed in clear water, and it's soaked for 1 minute in a wetting agent which eliminates all water spots. The film is then dried and it reveals its secrets. And here's the hologram created from the sculpture. A hologram really creates a three-dimensional illusion. Some holograms can be animated. They are generated from a series of still holograms. Depending on the complexity of the project, a hologram can be produced in between 1 and 5 hours.
Printing on packages isn't just the listing of ingredients or instructions. It's also the complex art of product identification, as well as creating an appealing, attractive look for the consumer.
All consumer products are packaged, and the making of these packages starts with the burning of an aluminum plate like this one. This animation illustrates the burning process, the transfer of an image onto an aluminum plate. The plate is placed onto a cylinder, and using a laser, the burning begins. The image appears in 6 minutes. This plate will make the printing impressions on packages. The laser which did the burning has to be perfectly calibrated using this test plate. The plate is now ready to make impressions via the offset method. Printing involves ink, and it requires selecting the right one. If the desired color does not exist, it has to be made up from a mix of various other colors. An ink trial is done with a spatula. And using this small manual press, color ink tests are done. The ink is spread onto paper and the color compared with the one called for by the customer. If the two match, the presses can be started up. This is a 6-color offset process printing press with a 72 by 108 centimeter capacity. The press is fed by a suction and friction process, devouring 8,000 sheets an hour. Now the printing plate is placed onto the press cylinder. This plate will contact inking rollers of the ink reservoir. To prevent it from drying, ink viscosity is maintained with this oscillator. The press starts up and reaches a production rate of 8,000 impressions in 60 minutes. The press comprises individual color printing units. The paper sheet passes from one unit to another, receiving a new color at each step. Here they register the colors, that is, the quality of the superimposition of the different colors. The final step is the folding and gluing of the boxes. This grooved plate makes folding point marks on the carton. And this machine does the cutting, the embossing, and stripping of the sheets at a rate of 6,000 an hour. The cutting die cuts the carton sheets and, together with the grooved plate, makes the folding joints. This sheet is slid behind the cutting die to equalize the cutting of the sheets. This enormous pile of 3,000 sheets is ready to be cut. The embossing press feeder handles between 6,000 and 8,000 sheets an hour. Rollers guide the sheets in the direction of the press. And here, the sheets are embossed by the machine. The precision of the embossing is then verified. Next comes the cutting of the sheets. This goes on at 8,000 an hour. The cutting unit strips and removes the unnecessary pieces, and the carton scraps are sucked up for eventual recycling. The scraps can also be cut away manually by using a hammer. And the carton end pieces are sent off for recycling. All that remains is the assembly of the packages. This high-speed gluing unit can make up 30 to 40,000 per hour. Gluing begins with the folding of the sheets, following the folding marks. The sides of the form box are then glued together. An average of between 5 to 8 steps are needed to fabricate a packaging box. Every day, this plant produces between 1 and 2 million boxes, requiring almost 4,000 tons of cardboard annually.
What would happen if you were severely burned on your hand, your face, your body? A piece of cultured human skin grown in sterile conditions would help healing faster and also lessen the scarring of the burn.
The culturing of skin allows us to save many lives. To grow skin, epidermis cells have to be isolated and made to multiply. It all begins with the removal of a small skin sample. The 10 million cells in this piece are enough to make a culture. The skin soaks in a medium containing penicillin and gentamicin, antibiotics which protect it from bacterial infection. Now a piece of skin is cut and delicately sectioned on a petri dish with a scalpel. The fat is gently detached from the dermis since it will not be needed in the culturing. The skin is cut into thin strips because thermolysin, the enzyme which separates the dermis from the epidermis, acts more efficiently on the small surfaces. Then, an enzyme destroys the links uniting the dermis and epidermis cells. This procedure is carried out in this incubator over 3 hours at a temperature of 37 degrees centigrade. Once incubation is over, the petri dish is removed from the incubator. Only the epidermis cells, also called keratinocytes, are retained. The epidermis is detached from the dermis with great precision. Now the strips are placed in a trypsination unit. Trypsin, an enzyme, will destroy the links uniting the epidermis cells in order to isolate them. This operation signals the cells to multiply now that they're in a favorable medium. In order to increase the effectiveness of trypsin, the trypsination unit is placed on an agitator. The cells do not have to remain in extended contact with the trypsin. They're inhibited with a medium containing serum. Then the liquid containing the cells in suspension is drawn off. Now the liquid is centrifuged to obtain two fractions. The base fraction containing the desired cells is at the bottom of the tube, while the upper floating fraction containing the trypsin has to be removed. This upper fraction is drawn off with a vacuum system. In order to eliminate all traces of trypsin, the culture medium is added to the base fraction and the whole is put back into suspension. Now the cells from the small skin sample have to be counted before being centrifuged a second time. The cells are counted by hand using a microscope or with this apparatus. The exact number of cells obtained during the extraction via a biopsy is determined, as well as the number of cells that will have to be seeded for maximum growth. The bottom portion of keratinocytes is divided in these flasks containing a culture medium whose composition resembles that of blood. The cells will multiply over a week in these flasks, placed in an oven at 37 degrees and at 8% oxygen. The medium in which the cells are immersed is changed every 2 days. In less than a week, the cells have almost covered the entire surface of the flask. They can now be trypsinated anew and thus reseed some 50 flasks, which in turn will be placed in the oven for about 1 week. Skin strips coat the inner surface of the flask. They are then detached with a spatula. The flasks are cut in two with a heating unit resembling a soldering iron. To make handling easier, gauze is placed on the skin strips whose thickness is less than 1/10 of a millimeter. The graft is placed on the wound. Clamps in the gauze will be removed after 10 days. A patient can be skin grafted in less than 2 weeks.
I'm a big fan of corn on the cob, but unfortunately, at certain times of the year, it's impossible to find. Thankfully, corn is also great out of the can. The journey from cob to can is quite something to see. Throughout man's history, food preserving has included smoking, freezing, drying, and salting. In the early 19th century, Nicholas Alpert built a factory to preserve foods in hermetically sealed glass jars and to sterilize them by boiling. But glass was breakable, and so in 1810, an Englishman named Durand invented the tin can, first used by the military in the War of Independence, and soldiers, it seems, first developed the handy can opener. The corn that's canned is harvested from mid-August until mid-October. Canning is done very quickly. Less than 4 hours pass between harvesting and canning procedures so as to conserve much of the nutritional value of the product to be sold. The unloading of many trucks of this size will be needed for the 136,000 tons of corn that are canned here annually. The cobs are transported into the plant on this conveyor. They will first have to pass through a kernel remover. Equipped with several counter-rotating cylinders, this unit removes the leaves and the silk which surround the cob. Within only a few seconds, the cob is completely stripped of its covering. Once clean, the cobs fall into this chute en route to the next processing step. Here they're lined up, ready to be handled by the kernel remover. The kernels are removed from the cobs by going through the machine where knives remove the kernels in a fraction of a second. Each of these units remove 1.5 tons of kernels per hour. Twice a day, the machines are stopped to inspect the blades, to clean and sharpen them. The corn kernels fall into the middle, while the cobs themselves are moved to the sides. Both kernels and cobs move along on their separate ways in the process. The kernels enter into this rotating drum, which removes any particles larger than the kernels. Nothing is wasted in the processing. Corn residues, leaves, and cobs will all be used later as animal feed. Now the kernels fall into a mix composed of water and of a fluid that's obtained when cutting the corn kernels. This liquid mix allows for the transporting of the kernels without damaging them. Next, the kernels flow along this belt and are placed on this conveyor toward the following processing step. Bleaching is done in this huge cylinder. A worm screw brings the bleached kernels to the surface. A visual inspection verifies the quality of the kernels. All that remains is to pack them into these leak-proof cans. Thousands of cans of every size are carried to the filling department. Filling the cans is done from this rotating filling machine. This filling machine can handle 300 to 450 cans a minute. The kernels which fall to the side are gathered up later in this cylinder and returned to the filling line. Here a brine composed of water, salt, and sugar is added. Covers are securely attached onto the containers, but the canning is not yet finished because they have to proceed with some very important tests. They perform tests in this laboratory that assure the quality of the product.
First, they check the water tightness of the cans. They also control the filling weight and the quality of the kernels. In the meanwhile, cans continue wending their way through the plant. One step remains: sterilization. Sterilization takes place in this oven at 121 degrees centigrade and lasts between 4 to 6 minutes. This is a crucial step because it guarantees that the product is reliable and that it will remain so for 18 months. Now they taste samples of the product to determine that it conforms to quality standards. Cans are labeled as customers' orders are filled. In this facility, they produce an amazing total of 43 million cans of corn.
I hope you enjoyed our show today. We wanted to take you behind the scenes into the world of manufacturing. I'm Mark Tewksbury. See you next time on How It's Made.
Today on How It's Made: hydroponic lettuce, construction wood, recycling, and fishing flies. Bet you thought the only way to grow lettuce was in a garden. Well, vegetables don't necessarily need soil. They can also grow in water, provided it contains the proper nutrients and fertilizers. That's called hydroponics. This method of growing hydroponic lettuce is called deep pool floating raft technology. It sounds pretty complicated, but it's really quite simple. And it all starts in the germination area with lettuce seeds. To plant them, workers use a steel tray connected to a vacuum hose. The tray has 276 holes, and the vacuum sucks a seed into each one. Next, they take a foam block with corresponding holes called an oasis and position it into the tray. A quick flip deposits a seed into each hole of the oasis. The seeds are coated in clay. Clay holds in moisture to nourish the seed, but also breaks apart easily to let the seed sprout. On the way to the greenhouse, the seeds get their first watering. Then workers set them afloat. The pool of water is about 30 centimeters deep. Technicians continuously monitor and manipulate its levels of oxygen and fertilizer. That's the key to hydroponic growing. The water is never discarded, just topped up to replace what the plants drink and what evaporates. On the first day, they water the seeds frequently. Within a couple of days, the seedlings start to appear. They water and fertilize them. By about the fourth day, there's some significant sprouting action. Again, they water and fertilize the plants. The first leaves emerge on about the 7th day in the summer. On about the 11th day in the winter growth rate is slower because there's less sun. At this point, it's time for the first in a series of transplants. Workers transfer the lettuces from the 276 plant oasis to a styrofoam board that holds more plants, 288. They set the boards afloat in the nursery zone. At about the 13-day mark in the summer, the 20-day mark in the winter, transplant number 2. This time to a less crowded styrofoam board that holds just 72 plants. This gives the plants more light and more room to grow. Workers use a hook to avoid damaging the roots. A plant needs healthy roots to absorb water and nutrients. The last transplant happens on about the 26th day in the summer, the 45th day in the winter. Now the lettuces go from the 72 plant board to a board that holds just 18. By now, the plants have long roots, so they're harder to manipulate. The lettuces go into the production zone, the last move before harvesting. These pools are bigger, so automatic machines move the boards around. This hydroponic system produces 500 plants per square meter, almost 5 times the yield of field-grown lettuce. And it's safer too. There's no need here for pesticides or fungicides. And because it's all indoors, fertilizer can't contaminate the environment. By about the 45th day in the summer, the 75th day in the winter, the lettuces are finally ready for harvesting. Workers cut off the yellowed leaves at the base, then either cut off the roots or wrap them around the stem, depending on how this crop will be sold. Then they vacuum cool each lettuce for longer shelf life. An American engineer has invented a self-mending plastic to use for components that vibrate and weaken. When the plastic tears, tiny capsules inside it also tear, releasing a liquid like blood from a cut. Then a catalyzing agent, also in the plastic, seals the tear like a scar. There was a time when if you wanted to build something out of wood, you had to pick up an axe and go chop down a tree. Thankfully, for city dwellers, all it takes today is a trip to your local renovation center to buy 2x4s, 2x10s, you name it. They start with logs cut from spruce or fir trees. Turning them into construction wood isn't that complicated. First, they soak the logs for about 20 minutes. This removes the mud and softens the bark to make it easier to remove. Next, the logs go through the debarker, a machine with a rotor that shaves off the bark. The rotor has 6 sharp blades that take just 10 seconds to shave a log bare. In the filing room, they regularly sharpen and inspect the saw blades they'll use to cut the shaved logs, straightening them back into shape when necessary. In this sawmill, there are 2 production lines. The wider logs go through this saw. The worker at the controls uses a laser to help him position and reposition each log as he runs it through the saw several times to cut it into as many 4x10-inch pieces as possible. An average log usually yields about 7 or 8 pieces. The narrower logs go through a different saw. This saw first cuts a board off each side, then sends what's left of the log onto another saw. The 4x10s on the first production line go for a second cut called the resaw. They're cut in half into 2x10s. The logs on the second production line end up here in what's called the Canterbull machine. It has 8 adjustable circular saws that can cut the log into various sizes of wood, anywhere from 2x3s to 2x8s, depending on the log's diameter. production lines feed to machines that smooth the edges and trim off any defects that can affect the strength or resistance of the wood. Then an automated sorter drops the wood into bins according to their size. Each bin then feeds the stacking machine. From here, they'll put the wood into a kiln to be dried to about 15% humidity. Then they'll grade the pieces and ship them to a lumber yard or renovation store. If you care about our environment, chances are you separate your recyclable waste from your other garbage and either take it to a depot or put it out at the curb for pickup. But have you ever wondered where it goes from there? When the truck arrives, your recyclables go through their first sorting. The worker puts paper and boxes in one receptacle, glass, plastics, and metals in another. At the sorting plant, the truck dumps each receptacle into a separate area. Then it's onto separate conveyor belts for more sorting. On the paper and boxes line, workers first remove any plastic, metal, or glass that got there by mistake. Then they sort what's left into 3 categories. First, corrugated cardboard, what brown boxes are made of. Second, newsprint. And third, mixed fiber paper such as cereal boxes, envelopes, and greeting cards. On the glass, metal, and plastics conveyor belt, workers first remove the big bulky items such as gallon-sized containers. A jumbo magnet picks up everything metal except for aluminum, which isn't magnetic. Workers then sort milk and juice cartons to one area, aluminum to another. They separate plastics into 3 categories, glass into 2, clear and colored. Once everything's been separated, each category goes into a baler, which compacts it, then binds it with wire like a giant bale of hay. Then it's off to the warehouse until they're sold to a recycler. At the recycling plant, they cut open a bale of plastics, then load everything onto the conveyor belt. The plastics pass through magnets to remove any metal that might have slipped through. Then it's into the shredder. It takes the shredder just 1 hour to shred 2 tons of plastic. All those containers are now tiny little plastic flakes. Next, cleaning by friction and water. Any remaining glass or other contaminants now sink to the bottom, while the lighter plastic flakes float to the top. The dirty water will be chemically filtered and used again. They dry the flakes by hot air, then put them into silos to be compacted. Inside the compactor, it's 160 degrees Celsius. The heat partially melts the plastic, fusing the pieces as they compact. The flakes go through the compactor's perforated inner drum, much like a pasta press, and come out looking a bit like macaroni. They're now officially recycled plastic in raw material form. Next, they're melted, pressed through a screen, then cut into pellets 1/8 of an inch long. They drop into water to cool, then go into a dryer. Factories buy these pellets and use them to make plastic products. This recycling plant takes the plastic flakes it produces to mold warehouse pallets. The mold goes in at 230 degrees Celsius for just about 7 or 8 minutes. It takes just 2.5 minutes to mold a recycling bin. Something to help ensure a steady supply of what the factory needs to keep producing recycled plastic. Still moping about the one that got away? Well, maybe you just didn't use the right fly. Fly fishing is one of the most challenging types of sport fishing, and tying a good fly to the end of your line can make all the difference. In about 300 AD, people began decorating their fishing hooks to mimic insects and small fish. The Macedonians were known to use a fishing fly made of red yarn and rooster feathers. Today, with so many synthetic materials available, the design possibilities are endless. But every fishing fly is still based on that centuries-old technique of attaching bird feathers or animal hairs to a hook. The whole idea is to trick the fish. The fly imitates an aquatic insect or tiny fish, something the fish you're trying to catch likes to eat. The fly maker starts by placing a hook in a vise. Using a tool called a bobbin holder, he winds a wax nylon thread carefully and tightly around the shank of the hook, then cuts off the excess. This fly will simulate a moth-like insect called a caddis, a primary food for trout. A caddis in the pupal stage of its life cycle, just before it transforms into an adult. The fly maker first attaches a special synthetic yarn to create the tail. He secures it along the middle of the hook. He then takes another synthetic material called dubbing to create the body. He spins the dubbing between his fingers onto the thread. The wax on the thread helps it adhere. He winds the dubbing over the base of yarn to form the body. Then he folds some yarn over the dubbing and attaches it with more nylon thread. Then he cuts off the excess. Good fishing flies not only look like the real thing, they also act like it, mimicking the insect's natural movements. When a caddis pupa is ready to transform into an adult, it swims to the surface of the water, then deploys its wings. The shimmering yarn on this fake caddis will give the illusion of the air bubbles this voyage to the surface creates. To simulate the wings, the fly maker uses dubbing made of deer fur. He cuts off the long, coarse hairs known as guard hairs. Then places them into a device called a hair stacker. He shakes it, turns it to the side, then opens it up. All the hairs are now evenly aligned. He measures the length he needs to create the fly's wings. Then he attaches it, leaving a portion sticking out in the front to form the insect's head. Next, he uses a tool called a whip finisher to tie a sturdy knot made of several loops. This caddisfly imposter is now ready to trick some trout. There are thousands of styles of flies. You choose which to use according to what the fish are feeding on at the moment. Fly makers use many types of natural and synthetic dubbings to form and decorate their flies. Feathers, animal hairs, metals, and plastics, often dyed brilliant colors. Tying a great fly won't always snag you the catch of the day, but if you maneuver the fly to make realistic movements in the water, the fish will buy it, hook, line, and sinker. Today on How It's Made. Personal watercraft, wine, particle board office furniture, and ice skates. They're to water what snowmobiles are to snow, what motorcycles are to road. The proper term for these adrenaline-pumping, wind-in-your-face vehicles is personal watercraft, but in Canada, most people call them Sea-Doos. The fiberglass shell that's the body of the craft is molded at another factory. It arrives here, ready-made. Workers use a template to position decorative decals on the upper shell, called the deck. Next, they install rubber foot pads on the steps. A robot drills holes in the lower shell, called the hull, first for the drainage system, then for the exhaust system. Next, workers install the straps that will hold the internal components in place. Then they install the rubber pad that goes under the motor. Next comes the motor mount to hold the motor in place. Finally, the motor itself. This 130 horsepower engine arrives at the factory fully assembled. It's a matter of putting it in place. Next, they install the jet pump. That's what gives the watercraft its jet power. Then the battery. Then the drive line. That's what links the motor and the jet pump. The 54-liter gas tank goes in next. They connect the drive line, then install the jet housing. That's a protective casing around the jet pump. Meanwhile, a robot works on the deck. It applies globs of glue in key locations. Workers stick on various straps that will hold internal components in place. Then the robot glues the circumference of both the hull and deck. They heat the hull to activate the glue. Then clamp the deck to the hull. The glue takes about 15 minutes to dry. Using an ultrasound machine, they inspect the seal to make sure it's watertight. Next, they install the hood and steering column. Now it's time to run an engine test. The last step is to install a plastic bumper. A roller presses it securely into place. Canadian researchers have invented a way to identify faraway objects, even in thick fog or complete darkness. They use a laser combined with military night vision technology to locate objects or people up to kilometers away. The system is so precise, it can read the name of a boat in the dead of night. The next time you enjoy a glass of wine, think about your place in history. Wine may date back to 6000 BC. Nowadays, we drink it from bottles, not animal skins, but the basic principles of wine making remain the same. Wine grapes grow best in temperate climates, but if grapevines are well protected, they can survive a Canadian winter. The riper the grapes, the sweeter the wine, so growers wait as long as possible before harvesting their crop. Pickers gather grapes by hand, cutting off the bunches with shears to avoid tearing the plant. For red wine, winemakers use the entire red grape, juice, skin, pulp, and even seeds. For white wine, they use just the juice of white grapes. While the winemaking process itself is certainly a factor, the quality of the grapes is what will ultimately determine the quality of the wine. Grapes are affected by weather, by soil conditions, and by how the vines are pruned during and between seasons. The grapes go into the crusher, then into the presser, which squeezes out the juice. Inside the winery, the result of all that crushing and pressing ends up in large stainless steel tanks. The winemaker adds yeast to make the sugar in the grape juice convert to alcohol. That's called fermentation. Winemakers constantly experiment with fermentation to try to improve the quality of their wine. They take samples of grape juice and mix them with different types of yeast. Yeast is found throughout the environment, in wild berries, for instance. They hydrate the yeast with a bit of grape juice, then pour the mix into the grape juice sample, let it ferment, then see how it turns out. The big fermentation tanks are refrigerated, and monitoring their temperature is critical. White wine must be fermented at 17 degrees Celsius, red wine at 30 to 35 degrees Celsius. The fermentation period depends on the type of wine. White wine has to ferment for 3 weeks, red wine for just 10 days. Rosé wine is somewhat of a half-breed, made with red grapes but fermented slowly, like white wine. It comes out pink. There's an extra step in making red wine. During fermentation, they drain the tank to aerate the wine. The oxygen helps the yeast work faster, over the short 10-day fermentation period. Then they pump the wine back in through the top of the tank to mix everything thoroughly. During fermentation, they not only monitor temperature, but also the sugar level. As the juice becomes wine, the sugar level drops and the alcohol level increases. Except for very sweet wines, fermentation is done when the sugar's gone, and the alcohol content is 11 to 13% for red wine, 11 to 11.5% for white and rosé. The wine is stored for a few months, then it's run through several pressure filters to remove any particles. Then comes time to bottle the wine. Large wineries have fully automated bottling plants, smaller operations, semi-automated systems like this one. The key in bottling wine is to avoid getting air inside, because oxygen turns wine sour. The colored wine bottles protect the wine from light, which can also affect the taste. People have used cork to plug wine bottles since ancient times, because it creates a tight seal that keeps the air out. Cork, incidentally, is a type of tree bark. It grows back so the tree isn't harmed. Inside the bottle, the wine continues to undergo subtle organic changes as it ages. Nowadays, you have to be pretty high up in a company to have a solid wood desk. Your desk is more likely made of pressed wood, an inexpensive alternative made from lumber byproducts. Particle board is a common type of pressed wood. Lumber mill leftovers provide the raw materials for particle board. The process starts with truckloads of sawdust. The next ingredients are wood shavings and wood chips from all types of lumber. They feed those chips and shavings into a large mill that works like a giant food processor, chopping them up into little bits. When the milling's done, the particles are between 0.2 and 5 millimeters big and less than 0.7 millimeters thick. To make the humidity level uniform, they put the particles into giant dryers whose combustion chambers are fueled by leftover dust from the chopping mill. After 15 to 25 minutes, the humidity level drops to 1.5%. From here, they'll send the dried out particles to a screening machine, which will separate them by size. Pieces too big for particle board are fed through the mill again. Sawdust becomes fuel for the dryers. Larger particles go into the rougher core layer of the particle board, smaller pieces into the smoother surface layer. Meanwhile, the factory's glue department gets to work mixing resin, water, wax, and chemical hardeners. Machines mix the glue and the particles, then push out a long, continuous mat. A cold compressor forces the air out of the mat. Then a hot press activates the glue and forces it all together. Next, a saw cuts the continuous mat into large sheets called masterboards. They're still hot from the hot press, so they're put aside to cool for about a half hour. Once the masterboards are cool, they're sanded. Then a stacking machine piles them about 80 sheets high. A saw cuts them into a smaller, more manageable size to be sent off to the furniture factory. At the furniture factory, the first step is to laminate the particle board panels with a decorative covering. First, the glue spreader covers the board surface with glue. Then another machine sticks on a 4 to 5 foot strip of decorative paper fortified with resin, varnish, and other chemicals. This covering comes in many different colors and designs, from solids to imitation granite or wood. A blade cuts the paper between each board. Then a machine stacks the boards to prepare them for cutting. The saw cuts through 6 to 8 boards at a time, depending on their thickness. The next step is to cover the edges of the particle board. They take a strip made of PVC plastic that matches the laminate. They glue it over the edges, then trim it for a neat finish. Next, they prepare the pieces for assembly. A multiple head drill makes screw holes in the panels. Meanwhile, they prepare the bag of hardware. There's a separate bin for each screw, nut, bolt, and connector. The machines count out the exact number of hardware each piece of furniture requires. Then the hardware is automatically bagged and weighed to make sure nothing's missing. Every so often, a worker assembles a sample to make sure everything fits together properly. If it does, production continues and they can proceed to packaging. They put together the particle boards for each piece of furniture. Add the hardware bag and instruction booklet, then seal everything in plastic film. From here, it goes into a box to be shipped to the store. Getting your first pair of ice skates is like getting your first bicycle. It's a childhood rite of passage, and one that leads to another well-known ritual, landing on your backside the first time you try them out. How long have we been ice skating? An iron skate found in Scandinavia dates to 200 AD. But people likely put blades made of bone under their shoes even earlier than that. Skaters tied on their blades with straps until the advent of the skate boot in the early 1900s. Today's skates are lightweight and high-tech and are designed for specific sports: figure skating, speed skating, and hockey. It takes 145 steps to make this high-end hockey skate. The skate boot is made of a synthetic material that looks and feels like leather. Once they've cut the pieces that will make up the boot, they shave the edges, thinning them out so the boot won't be bulky, particularly where there's overlap at the seams. They position a reinforcement piece onto what's called the quarter, the main structural piece that will form the sides and back of the skate boot. They glue it on with a hot press. The boot pieces now go to the sewing department. They stitch together the tongue piece. Then, using a sturdy zigzag stitch, attach the quarter and the heel piece. They spray glue on the quarter and on the ankle support. Then they stick on a foam ankle pad designed to mold to the contours of the skater's ankles. Next comes the lining. They must center it perfectly for the skate to be properly aligned and balanced. The eyelet machine works like a hole punch, punching out eyelets in the quarter. They reinforce each eyelet with an aluminum washer. The last step in the sewing department is called forming. They place the boot over a metal foot form. A hot press laminates the boot to give the back and sides of the quarter their shape. In the assembly department, they put the parts together using a foot form. They tack on a white plastic insole and a black plastic toe cap. They brush on a layer of glue and attach the boot. They sand the bottom of the boot to roughen up the surface for better adhesion. An automated machine applies a layer of glue along the contour of the boot's underside. The boot then goes through a heat machine for a couple of seconds to evaporate the solvent in the glue, making it tackier. As with the lining, they must position the sole perfectly, or they'll throw the skate off balance. An 8-ton press presses it onto the boot. The sole is made of strong carbon or carbon composite, depending on the skate model. Once the glue is dry, they drill 2 holes through the sole for attaching the skate blade. The blade sits in a plastic holder. They screw it in place through the holes, then secure it with 5 steel rivets and 4 more resistant copper rivets. Like the lining and the sole, the blade's alignment is crucial. Roller hockey skates are made almost the same way as ice hockey skates, only instead of a blade, they attach an aluminum chassis with rollers. In the finishing department, they inspect the inside of the skate, checking the blade holes and rivets in particular. They plug the blade holes. Then they lace up the first 3 sets of eyelets. Finally, they install what's called the footbed, the high-density foam padding that lies under the foot. Last but not least, they clean the skate, trimming excess threads and removing any glue residue. If you have any comments about the show, or if you'd like to suggest